Hello, and thank you for joining us for this latest AMS webinar with ABB. My name is Simon Duval-Smith and I'm the Associate Editor of Automotive Manufacturing Solutions magazine and Chairman of the Automotive Manufacturing Solutions conferences. Today, Didier Roual, I hope I say your name right, Didier, who is Manager of Paint and Sealer Process Engineering for ABB, will be demonstrating ABB's new and robotic paint systems. These are driving higher efficiencies in paint processing methods, and today we'll specifically concentrate on exterior car body painting. ABB has many other technologies to deal with other parts of the car and the process, but today our exterior car body painting. Didier Roual is very experienced in the painting industry, and he's been what he calls playing with paint and robots for the last 26 years. He has a great deal of experience in many areas, including process development, sales support, site management, research, proposals, project management, marketing, product management, and engineering management. So before I pass over to Didier, I would just like to remind you all of you in attendance, to draft up some questions, make a note of some questions, which Didier will answer in the question and answer session following his presentation. Please ask your questions by typing them into the box in the lower right-hand side of your screen. If you should have any technical issues during the session, please also type these into the question and answer box, and our team will do their best to sort these out for you. So, from AMS and ABB, we hope you'll find this webinar stimulating and informative. I'll now hand you over to Didier to begin the presentation. Thank you. Didier.
Good morning, everybody. Well, Simon, thank you very much for the nice introduction. I'm going to start the presentation right now. And so, as Simon was saying, we are going to focus today on the exterior car body painting. The development that we have done is really was started with the exterior car body painting. We will talk in another webinar probably about interior painting and Cartridge Bell System atomizers, but for right now we'll just focus on this. First, one quick slide for those who do not know ABB. ABB is divided in 5 global divisions, and robotics is belonging to the discrete automation and motion divisions. As far as robotic paint business is going, we are located in many countries, as you can see on this map. We have operation in most area with industries. ABB is producing a complete portfolio of paint-related product. We have explosion-proof robots, we have motion and process controllers, we have our own paint atomizers, and we have all the softwares that we need to control efficiently a paint system. We also have very efficient offline programming tools. And we put all those nice products together to make a complete robotic paint system. So you see here on the screen an example of what it looks like when we put it together. So what I'm going to talk about is our latest development in exterior car body painting, and this is we call the 3rd generation of robotics. And I'm going to clarify that. The 1st generation, we had a robot mounted on rails, and they were kind of at the floor level. And with this, the spray booth was 20 feet wide, which is about 7 meters wide. We had programming done with a teach pendant with buttons that we were pushing. Not easy to program. Absolutely no offline programming tools. 2nd generation of robot came around where we were trying to reduce the width of the spray booth. So with this, we were down to something closer to 4 5.5 meter in width. We had a more sophisticated panel, and we could see the beginning of offline programming tools. The third generation is a little bit different. We have robots mounted on the wall of the spray booth. They are not moving with rails, they are stationary. We have now to program very sophisticated and nice teach pendant with bright color screens. Actually, it's almost like a video game station that you've got in your hands when you're programming that. And we have like offline programming tools that are very powerful, letting us creating all programs before we start programming anything with the robot itself. So what's so special about this generation of robot, and how can a robot work in a narrower booth? How can we make a robot work in a narrower booth? So I'm going to play, it was supposed to be videos, but on a webinar it does not work very well. So I have little animations here that are going to explain how this robot has a unique kinematic that let him work in a very small booth with bigger arms. So it's a little bit of a contradiction. We increased the size of the robot, bigger and longer arm, and now it's able to work in a very narrow booth. So in this little animation you can see here how the robot moves, and when it moves along the car, here the back of the robot, this is a classic kinematic, is touching the back of the wall. So it doesn't matter where you put the robot, either it's on an elevated rail or the robot is mounted on a lower level. When it gets to that point here, this is where the robot is. Either you need to have a bigger spray booth, or you need to have the robots on a rail and you're driving the rail up and down, so you never have to go through this position here. Now let me show you how that works with the new kinematic of a robot. Robots are mounted in a different position and the kinematic is different. Now you see the robot on the left side is going to paint the side of a car, and the robot on the right side is going to paint a hood and a roof, horizontal surfaces. So you can see how the robot is working now. The robot is working parallel to the booth wall. It never tries to go into the wall. It's just working like that. And the same thing for the robot painting the hood. The elbow of the robot never tries to go through the spray booth filter. So that's what makes the big difference for this robot, the kinematics. Longer arm, working in a very small spray booth. So if we look at this robot, many features, but we're going to focus a bit on interesting features because those are the features that are impacting your spray booth size and your production throughput. We're going to talk about high acceleration, large work envelope, and working without a 7th axis. What are those really doing when it comes down to designing a spray booth or a spray system? So the way we program the robots, there's 3 different ways to program robots at ABB. We have the classic programming methods. So let's say on this screen here, you can see this little blue box surface. This is what I'm trying to paint. And in this view, you can see the robot motion. So I have a little tracer here that will show you where the robot has to move the atomizer. And the atomizer turns on and off every time it's changing direction. That's the classic way to program robots. We have developed another way where the robot stays on the part and the trigger stays on, so we call it stay on. So with this, it's quick to understand that you get a shorter cycle time because you travel less distance. You're reducing the overspray and you're reducing the paint consumption. So I had a question many times, everybody's asking me, well, why didn't we do that before? What's so new? Why don't we just do that all the time? The answer is very simple. It's all related to the acceleration of your robot. When the robot is reversing direction, if the robot is slowing down, it's going to drop a lot of paint on the surface. And that will look something like that on the right. As you increase the acceleration capability of a robot, it's getting flat because the robot does not have to slow down when it's reversing direction. So that's one big impact. Having high acceleration on a robot will let you keep the atomizer on and turning around on the surface to be painted, and you don't drop a lot of paint. The second impact of high acceleration is the cycle time. If you look at this slide here, it's very easy to understand that to achieve the exact same distance, if you have acceleration available, you're going to travel faster. So we can see here on a simple program that could be a hood or half a roof on a car, already 2 seconds of cycle time difference, just from the acceleration. Do we need a 7th axis on a robot like that? Now let me show you a little cross-section here, and you're going to understand where I'm getting with. This robot is not moving. I put a car here that's around 4 meters in length, just to give you an idea of the scale of what this robot is able to do. So this robot, from a stationary position, is able to paint on the side of a car strokes of 6 meters long. We don't have that many cars that are 6 meters long right now, but when the car's moving, that's enough to let us paint the side of the car. This is what really makes a big difference in the way we program. I'm going to explain how we use this large work envelope to improve cycle time and paint quality. Let's say I have to paint the hood of this car here, and a classic way to spray it is you will split it among the left and the right robot. So right now I can see a robot on the left side of the car spraying half the hood, and I have a robot on the right side spraying the other half. Now what I have to do with those two programs, left and right programs, I have to kind of do some stitching to join them in the middle. Usually this area, this is where we have trouble with quality. Either we have too much paint, not enough paint, not distributed correctly. So, and it's right very visibly on the front of the hood. Another way to do it would be to just paint completely left to right, like that. Complete the entire panel, no interruption in the middle, no junction, no stitching. To do this, you understand you need a large work envelope. So, not only you get a better quality, but here also, here's the impact of the cycle time. If you do 2 programs versus 1 program, using the exact same application parameters, same speed, same acceleration, there's a 4 seconds cycle time difference here, just on 1 panel on the car. So you understand here the impact on the cycle time. Now let's talk about quality on the car. As you are making the stitching on this panel here, you're going to have little bumps and little valleys here. And here on this model, this is kind of the best you can get. It's really close to the best you can get here. So you can see that not stitching the programs or no patching with multiple little programs makes a more smooth and even distributed layer of paint. So here's a little recap slide where you can see the many ways we can program a car with robots. And there's many good ways and many ways that are not that good. So here's a little highlight on, in green, this is what we want to do to improve cycle time and have good quality. And only a large work envelope robot will let you do that. This is how it looks on the car when it's programmed. This is the path that you will see covering the entire side of the car, front to back, covering the entire hood, front to back, and same thing with the hood, left to right. with paths that are a little bit curved to follow the hood here. Same thing on a bigger car here. You can see the distribution with a left and a right robot. So this is all about having the work envelope and the reach to be able to do that. So we talked about the classic. I just covered in very details the stay-on. There is another development that we have done to reduce cycle time and footprint is what we call variable pattern. So before I talk about variable pattern, I'm going to introduce you to something as important or more important than the robot is the atomizer, what we use to spray the paint. So the robot here we can see has a large work envelope, high acceleration. This atomizer that we developed called the RB1000 has a very high flow rate. This atomizer has a very powerful turbine. It's very powerful overhaul. So this little slide here kind of explain what we were looking, where we were designing. We wanted to expand the operating windows of Atomizer. You can have a very good robot, but if you have an Atomizer that sprays the paint well, the robot will not do much. So if you look on this slide, you can see where I would say current product or some of the products are on the market here. When you're reaching 500 cc flow rate, you're starting to stretch really what you can do, and your operating window is narrowing. And we are now able to spray in the 1000 cc area. As you can see on this illustration, the window is a little bit narrower, but still we were not able to go there. So now what it means is we're really comfortable spraying flow rates of 700, 800 cc's, and we have already a few systems working really close to 1000 cc. What's important to do that is to have a very, very powerful turbine and air motor. So this is a rotary atomizer. The little bell cup that you're seeing on the screen here, if I may, find that here. Second here, my screen disappeared on me. All right, let's go back here. Sorry about this little technical glitch. So you can see on the screen here this bell cup at the front of the atomizer. This is rotating at very high speed, 60, 70, 80,000 RPM, and we put paint on this bell cup and the paint is atomized this way. What's very important for an atomizer is to be able to rotate fast, to handle the load of the paint coming on the bell cup, and also now a new element in the design is we have to be able to handle the acceleration of the robot. So the robots are producing a lot of accelerations now. So classic atomizers, when you put them on this kind of robots, they would not survive. They are not able to handle the acceleration. Another key features of this robot is the ability to control the pattern size. And a little animation here, you can see this atomizer spraying a very large pattern, and then it's switching to a very narrow pattern you can see here in the center, and now going back to a very large pattern. So with this ability to go narrow and wide, we're going to improve the way we put paint on a car. We can put paint in a much faster way and use less paint. So let's talk about the programming for variable pattern. You understand this atomizer is able to spray a large and a small pattern. So what we are going to do is we're going to use both patterns. a very narrow pattern. Here you could see it on the screen, it would be like the red line, because then when I'm on the edge of my panel here, I will not have a lot of overspray. Then when I'm in the center of a panel, here represented by the yellow line, I will use a large pattern, which is a lot more efficient. I can put out a lot of paint in a very efficient way. So this is how it looks on a car body. This is an actual program here that I have edited for the presentation. You can see on the bottom of the car the red path going with a lower flow rate and kind of a smaller pattern. Then we go to the yellow path. We will have three passes with the yellow parameters here, going a little bit slower and with a very large pattern. Then when we get to the top of the car here, we get back to the smaller pattern, and with this we're able to cover the entire side of the car and have a very, very efficient and fast way to program. Now let me quantify that. If you look at this car, this is the exact same car, big SUV. On the top we have the classic programming methods on that. To paint that one car, let's say if I leave that one car and I have to paint the entire car with one robot, okay, it will take 440 seconds to paint that car. Now if I use this new programming method, the variable pattern, okay, I'm able to spray that car in 264 seconds. So on a car on the line running at about between 38 and 45 jobs per hour, the 440 seconds means I need 5 robots to do it. The 264 seconds means I can do it with 3 robots. It's a big difference here. So this is how it looks when we install those robots. This is a spray booth that you can see here. We can see the RB1000. On this window, it's for primer. It could be also the same configuration for base coat. And what you see, the Atomizer here is a Cartridge Bell System. We don't have a paint line actually going to the Atomizer. We are loading small cartridges of paint in this Atomizer. You will notice also there is no rails. The robots are mounted stationary on the booth wall. The first zone that you see right in front of us with the 6 robots is to paint the exterior. And the zone that's a little bit more down on the line with 8 robots, this is doing the interior of the car, painting the doors. So that will be probably our next webinar on paint. How do we do interior painting with stationary robots and moving line? This is how it looks with the clear coat spray booth. See, the Atomizer is different. We do not have the cartridge loading on the back of the Atomizer anymore. Exact same layout, same configuration. So with this robot, you understand that we are able to design what I would call subcompact spray booth. We can mount the robot in a position like you see on the screen here. We call that a cluster mount. In a very narrow spray booth, you can see here the tracers of where the robots have worked. We can spray an entire car here in a very narrow, short booth. So it's a big difference when we're migrating from rail robots that takes more length and more width than this robot. So again, I'm going to try to quantify that for everybody here on what is the impact of this robot on the design of a paint line. If you look at this basic design here, it's a classic concept where robots are mounted on the rail, and we have a multiple zone for exterior and interior painting. So when we use the 5500 robot, the first thing we can do is we can reduce the width of the booth, going from 5.5 to 4.5 meters. And that's giving us already 15% of reduction. Then after that, what we can do, we can reduce the length because we don't have a rail. Robots, when they work on the rail, they have to manage their position related to each other. So you always need a little space between the two robots so they don't run into each other. When the robots are not mounted on the rail, you can put them really close to each other. Everybody knows where everybody is. Very easy to program. They can work in a very confined space, close, 4 robots in the same area. Absolutely not a problem. You don't have to manage. You know exactly where the robot is at every time. Programming is easier. So with this, we're able to reduce the booth lengths. And here, that's a 25% saving in the footprint. The next thing we can do is, because the robots are more compact, do not need a rail, on the interior painting, I don't need 2 zones. Right now, I have 2 zones because it's very difficult to put 6 robots in one small zone, because when you have 3 robots on one rail, that drives the length. And since it drives the length, might as well have 2 zones. So here you can do everything in one zone, and that's reducing the footprint down to 37%. And another option that you have is compared to this one here. In this one, you can see that let's start on the right of the screen. The first zone is at the bottom here is the interior painting zone. Then the second zone is the first pass exterior. Then you have an empty zone where flash off. It's time that we need to have between the 2 layers of paint, and then we have the second layer of paint with the last zone. So what we can do here is in the layout is we will use the interior painting as the flash off zone. So this empty zone with no robots just disappears, and that further reduces the footprint to 41%. So if you look at this slide here, you can see the complete steps all the way down to the footprint. And by the way, this is to scale, so that gives you an idea of the footprint impact when you use this type of robot and this type of atomizer. This is a lot of savings. Another thing I want to point out is there's so much flexibility in this robot and the way you can use it, that when we are studying projects, here's an example of a study we've done, there's so many options we can look at, and that makes the design for optimization and creating the perfect layout a lot easier when we're designing the lines. So here I'm going to recap a little bit with the slides in here. When we design a complete system, what is the impact and what's the synergy that we have between all the product and all the process and all the concept that we are using? So in this, there's a few concepts that we have not developed yet, but you will understand for the one we've talked about. When you use one type of robot, because we are only using one type of robots, this same robot is doing primer, base coat, clear coat. The same robot is doing interior, exterior, opening door, closing doors, hood, same machine for everything. It makes everything just easier, where a lot of robotic system will use 2, 3, sometimes 4 different types of manipulators. It's exactly the same for Atomizer. The Atomizer that we use is the same for base coat, primer, clear coat, waterborne, solvent-borne. We use interior, exterior car painting. We use the same Atomizer for all the application. So the big reduction here in training, in parts, and maintenance, it makes things more simple. We do not use 7th axis. We have paint lines running up to 80 cars per hour, conveyors moving 10 meters or 30 feet a minute. So very fast lines without 7th axis. So it's not related to your conveyor speed. It's just the way you use the robots. So when you don't use the 7th axis, you actually have less parts. Very easy to understand. It's more simple to program because you don't have to manage the 7th axis. You don't have to manage the collision between the two robots. Maintenance is a lot more simple. those rails are high maintenance, especially the cat tracks with all the paint lines that are stuffed into the cat track. Cycle time is reduced. You never have to bring that robot on a rail back at home. It's always sitting at the home position, not moving. And because of not using a rail and the robot being efficient, you're able to reduce the number of automation points, smaller footprint. The stay on a variable pattern, it's really reducing the cycle time, reducing your paint usage, and there's a slight increase in production capacity. In exterior is a concept we have not reviewed. That will be for our next webinar, but it's really something that reduces your footprint further. And paint equipment sitting outside the spray booth. For most applications, we use Cartridge Bell Systems, which means on the arm of the robot, there's no paint line. There's no controls. Everything is done outside the spray booth. So robot comes back and gets a cartridge to work in the spray booth, and there's absolutely no equipment mounted on the robot. Clean coat concept is not something we have not reviewed on this presentation, but it's equipment that we install on the Atomizer that reduces or eliminate the contamination. It's increasing the time between manual cleaning. A Cartridge Bell system, you see on this small illustration, it's the most simple waterborne system on the market. What you see on the picture is pretty much what you need to work. 2 cartridges and an atomizer. There's nothing else. Very simple. It's more simple than a system with a classic color change and a gear pump. A great reduction of paint usage here because the paint is never in paint lines. So the cartridges are dispensing the paint directly into the bell cup. There's almost no waste on color change. There's no paint line again to clean. And that improves a lot the transfer efficiency, having internal charge on waterborne, and that's further reducing the requirement for having more robots because of less efficiency. So if you combine all those features together, that creates a lot of synergy here, and this is where it's becoming very powerful, compounding a lot of benefits where it comes to, for example, cycle time reduction or footprint reduction. We can really quantify that, and if we were not using this type of robot and this type of atomizers and the advanced programming methods that we have, a lot of the installations that we're putting out would require more space, more robots, and would not be as efficient. This is concluding my presentation, and I'm just going to hand it over to Simon for question and answer.
Thank you very much, Didier. Thank you. Yes, a question that comes up, I think, is that just can you tell us a little bit more about how significant and how important the change from the robot rail is? I mean, you talked about saving space and time there, but what about actual cost savings in the long run from switching from rail? Just the key points, the size of the booth, the actual rack expense of the rail and so on. Please.
Yes. Thank you, Simon. Yeah, this is a question that we get a lot, actually. What is the actual impact? Well, one simple answer to that, just think about this robot that you have in a booth as a mass, not as a robot. Just so a robot is 600-700 kilograms. Okay? And just think about a servo motor that is just there moving these 607 kilograms up and down on that rail all year long. So what this motor is doing is just moving 700 kilograms back and forth on the rail. Just multiply that by the quantity of robots, hours of operation. That just tells you how much energy you're just wasting on moving that robot up and down. So there's one big thing on the operating cost is moving this mass back and forth. The second thing is like you said, because you don't have a rail in the spray booth, it's easy to design a booth that is a bit narrower. Also, the design of the spray booth is a lot easier. Robots are just mounted on the booth wall, a little bit of structure outside to hold on to the robot. So that reduces the cost of the steel structure to support the robots and the booth itself. And when it comes to efficiency, not using a rail made us change the way we are programming a lot of things for a more efficient way. Programmers would have a tendency to follow the car and try to complete what they are doing with the rail robot. And that drives travel length on the rail, that drives booth length. Well, when the robot is not moving, you have to think differently and you work differently. And so you spray the hood when it's in a good location to be sprayed and to be started and completed. And then as soon as you're done with that, the car is in a perfect position to get the entire side painted. So it drives efficiencies because a robot is not moving up and down the booth, so the booth stays smaller. And since the car is moving, the first question is, since the car is moving in the booth in most installation, why do you need to also have the robot move? It will be like a car wash, you know, just let the car move or let the wash move and just wait, and you can access all the panels. And also, we haven't talked much about stop and go. That's another presentation we could have on comparing and analyzing the difference between a moving line conveyor and a stop and go. But in a stop and go, we see the exact same thing. We can design a smaller compact booth with all the robots that's required in the booth with no rails. Is that answering the question, Simon?
Yes, thank you very much indeed. Thank you, Didier. Yeah, as you say, why move the car and the robot? It seems crazy, actually. If you're looking from outside the industry, it would seem a crazy solution. We've got quite a lot of questions now come from all over the world. And one of them there, Diego Garcia, I'm not sure which company you're from, Mr. Garcia, but thank you very much for the question. You say, do you have any comparing appearance data? I think here Diego means, do you have any actual application data in comparison to existing setups and to the new setup? So perhaps that's something more in-depth. Maybe you can liaise directly with Mr. Garcia, please, Didier, on that one.
Yeah, I can answer.
Which you will be able to do after the webinar, no problem. The other question is from India, I think, from a Mr. Anand Shinder. I'm not sure which company it's from. It's saying, is it possible to retrofit on an IRB 5400 and an IRB 5400, your older robot? Is it possible to retrofit the new generation Bell? Can you tell us about that, please?
Yeah, absolutely. On most of the RB 1000 are retrofitting on the 5400 robots. The first generation of 5400 robots might be in some limitation here, but on most of them, yes, it's possible to retrofit. Absolutely.
Thank you very much indeed. That is a testament not only to the adaptability of your products, but also the longevity of an ABB robot. It lasts so long that you have to retrofit. So I'm sorry you can't sell a new robot every time, Didier, but that is a testament, as I say, to the quality of your products. Mr. Anand Shind actually has kindly told us he's from Tata Motors in India, so thank you for the inquiry, Mr. Shind. Another question from him also, a couple more. Can you give us the percentage of solids that the gun, he says, I think he means the Atomizer can handle? What kind of solid thickness, or is that something you need to follow up later?
No, I can answer that. Solid content. It is my experience that the solid content of paint is greatly varying in different areas of the world. Working in Asia, working in Japan, Australia, South America, North America, it's different. In North America, solid contents are very high. They're a little bit lower in Europe, and in many parts of the world, it's even a lower solid content. For waterborne paint, we would handle low solid content as low as 15 all the way to a 40% you find on primer, And for solvent-borne, it can go as low as 10% solid content I've seen on some paint lines, and all the way to 50% that we would see on a clear coat. So here again, the solid content is driving the amount of paint that you need to put out, because when we say it's 20% solid content, we mean only 20% of the paint might remain on the car, less the transfer efficiency. So I hope that this is answering the question, but yes, we can handle any kind of solid content.
Thank you. Mr. Schind also asked the paint resistivity for high solid paints. How much can it handle? Not quite sure I understand paint resistivity, resistance. Do you understand that? Sorry.
Absolutely, absolutely. So a little clarification for waterborne paint with high solid content, absolutely not a problem. What we are using is a cartridge bell system with full isolation, no high voltage fault there, absolutely not. When we use the same system for solvent-borne, same problem, same solution, absolutely not a problem with the resistivity here that would create high voltage fault from paint line tracking or grounding. There's a range for resistivity of paint, especially for solvent-borne paint, because solvent paint can be adjusted. The resistivity can be adjusted depending on the blend of solvent. So we have to we're always working with the paint suppliers to find the happy medium between a paint that is just conductive enough so it will get the full charge of electrostatics or high voltage, but it will not be too conductive so it would create fault in the paint line that brings the paint to the atomizer. So I hope that's answering the question, but yes, we can work with a pretty wide range of I would say conductivity on paint.
Yes, thank you. Yeah, conductivity. I hadn't realized he was talking about electrical resistance. Thank you very much. We have a question from South America from a friend of AMS, Mr. K.O. Bertolini, who is a paint engineer at Ford in South America. Nice to hear from you, K.O. And K.O. attended our conference, the AMS South America conference. And he asks, could you tell us a little bit more about the CDS system, about the cartridge system? Do you have some videos of this system being used? And can you follow up with KO afterwards on this, but just tell us a little bit more about it, please, Didier.
Okay, the Cartridge Bell system is something that we have developed starting, I think we started this activity in the early 90s, and what we have done with this is removing the paint line that goes from, I would say, a paint, there's a big paint line, a pipe that goes and bring the paint to the atomizer. Instead of doing that, what we do is we take a little container, we fill it up with paint, and we put that container on the atomizer, and the paint is dispensed directly right from there. So it's a little bit like with the difference, like if you're spraying with a spray can, it's really close like to that. We just have to use the paint that's in the container, and then when it's empty, we get another container. So this system works very well. This is the most simple waterborne electrostatic paint system available on the market today. This is just very simple to use, and it works very well. We have more than 1,000 of those installed. So if there was a problem with it, I think we would know. Works very well, very efficient. The dosing system is a volumetric servo controlled, and the servo motor is actually not located in the atomizer, so the atomizer remains compact and light, and the servo motor is located outside, and we're just using like a dosing liquid to push the paint out. So the paint is loaded in a chamber. On the back of the chamber you have a little piston, and you're pushing that piston with another liquid. The CBS will be the subject of another webinar. It's this product on itself, it's an entire session to understand how it works, and the benefits are huge.
No, absolutely, thank you. Yeah, no, I mean, of course, as we all know in the world of paint shop, which you can read about in our magazine, Automotive Paint Shop Solutions, which comes out twice a year now. There's been a lot of debate between Cartridge Bell Systems and pump systems. And yes, as you say, Didier, that's certainly worthy of another whole explanation. So I do hope you'll come back and talk to us more about that. We've got lots more questions here. One from a Mr. Igor Pushkart. I hope I say your name right, sir. You say, do I need to be carrying out the calibration of the robots, and which program is best to use? Can you tell us a little bit about the software integration there and the calibration, please, Didier?
Okay. I mean, all robots are explosion-proof. EX robot, they are purged. So when we first start the robot, we're using intrinsically safe signals to the robot to check where the axes are, and then we are purging the robots, and then the full control system takes over. The robots are calibrated when we manufacture them and install them, okay? After that, they should not be recalibrated unless you change the motor or you break something mechanically. There's no need for recalibration. There might be a need for resyncing the robot, and because on the travel of one axis, let's say for example the rotation of the robot, the base, when you go let's say 90 degrees on the base, the robot is doing multiple rotations. We actually do not have anything that tells the robot in which rotation is in. So when we start the robot, the software keeps track of the rotation on the robot. So if for any reason it loses track of the rotation, you have to just bring the robot through some markers. Doesn't have to be super precise, just bring them close to the markers and then resync the robot. You don't need a tool to do that, and then the robot will restart from there. I hope that's answering the question.
Yeah, no, thank you very much indeed. Yeah, yes, we've got lots of questions here. I think one from a Mr. Nirmal Babu. Again, I hope I say your name right, sir. He's asked a few questions here, but I think if you can just tell us a little bit about the benefits of the transfer efficiency of the RB1000, and maybe also he's asking about when we procure ABB robots from you and the facility, a booth from another supplier, how do you integrate it all, and and how can you provide support for the installation?
All right, so there's 3 questions here.
Sorry, I'm sorry. Yeah,
but that's okay, Simon. I will take those. We'll talk first about the transfer efficiency. Then we will talk about integration with booth integrators, and then we will talk about support, if I understand. So let's start with transfer efficiency. Transfer efficiency of an atomizer can be measured in a few ways. I would say more important than the transfer efficiency is the paint usage. And I'm going to try to explain that quickly and simply. You could have a system with high transfer efficiency, but the paint usage is high. And let me clarify that. If you are painting something with a very powerful electrostatic systems, and you are spraying a lot of paint on the car, the paint might end up in areas that you don't need. Let me give you an example. You're spraying the side of the car with a large pattern and using electrostatics. The paint will go in the wheel well, the paint will go in the area where you have the light, the paint will go in the area where you have a bumper or a fender, the paint will go through the windshield and through the door on the floor of the car. You don't want the paint to go there, no added value. But your transfer efficiency could be very high because all the paint gets on the car, but it doesn't get on the car where you want. So what's important is to have a system that is brushing the paint on exactly where you need it. So I've seen a lot of systems on the markets that have like atomizers with a little bit of a bigger pattern, and they are very efficient. I mean, the paint gets on the car, and they get transfer efficiency like up to 85%. But they are measuring that by measuring the weight of the car. So they take a car before painting, and they say, okay, 900 kilograms, and they put the paint on, and they put it on the scale again, and 910 900 kilogram and 20 or 30 or 40 or grams or whatever panel we were measuring, and that's how the transfer efficiency is measured. Now, out of that paint that's on the car, maybe only a fraction is where you need to have it. With our system, we're really brushing the paint where it needs to go. So your paint usage is much lower. Transfer efficiency is high, but also paint usage is really low. So if I want to illustrate that and give you an example, let's say I'm painting a car, and when I'm finished painting the car, I've used 1000 cc to paint that car. Okay, and my transfer efficiency was 50%. So if I use 1000 cc, 50% transfer efficiency, I've put 500 cc's of the paint on that car. Now, if I take the atomizer at this point, I go through the windshield and I sprayed inside the car another 1000 cc. Now that 1000 cc, almost all the paint will get on the floor of the car. I get out, and now if I measure the transfer efficiency, I'm probably not at 50 now, I'm much higher, I'm at 75%. But I've used 2000 cc's, not 1000. So in one case, I used 1000 cc of paint, and I have 50% transfer efficiency. In the second case, I put another 1000 cc of paint on the floor of the car, and my transfer efficiency is much higher now, but my paint usage is also much higher. So I'm trying to explain here that transfer efficiency is an important number. This is not what our focus is. Our focus is more on the way we program to really put the paint only where it needs to go, and this is where you get the real saving. That was the first question. The second question about integration. Yes, we are working with many companies. We have integrated a robot with Dürr, TKS, Eisenman, GK, and a lot of companies I don't even know worldwide. We are really working very well with all integrators at putting the system. And actually, our robots are very easy to install, not demanding on the structure, very light to manipulate and bring into the spray booth. So I don't see any problem from my perspective in working with integrators. And the third question was about support. The installation of robots in different locations in the globe is driving the location of, I would say, support centers. So if I go install a robot on an island in the middle of the Pacific, I might not have a support center close. Now, if on this island I start to have 100 or 200 robots installed, I might open an ABB office on that island, and I'm sure I will have a lot of volunteers to go there. But this is driven that way by market size, market requirement. We have automation centers located in almost every country with, I would say, field service support. Simon, I hope I answered the three questions here.
Yeah, no, great, thank you. Mr. Nirmal Babu is a very prolific asking questions, and yeah, I think I would ask that you must follow up with him, because he also asked specific questions about the unit cost of 5500 and of an RB100, but I think that's probably better for you to follow up after the webinar. He also asked a specific percentage of transfer efficiency, but as you've just explained, this is a slightly different approach. So I'm sure you can follow up.
I can have numbers for that if we want right now for specific numbers.
Well, I'd like to get through some of the other questions if you don't mind, and if Mr. Babu doesn't mind, because they're coming from all over the world. You see, I don't want to miss anybody out. From a Carrie Zhu, I think is in China. Carrie, I'm not sure which company you're from. Do forgive me. Is there any influence and contamination to the second exterior area when you paint the interior zone between the two exterior zones, and if yes, how to avoid it? So,
I'm going to. Yeah, I understand that. This is a question asked many times, and typical paint application. We spray the interior of the cars, manually or with robot, doesn't matter. As we do that, a little bit of paint overspray gets on the exterior of the car body. And then we kind of, it's kind of a dry dust that's deposited on the surface of the car. We kind of cover it up with the 2 layers of exterior coating. Now, when you're painting, like in one of my examples, painting the interior in between the 2 layers of paint, the concern is, am I able to cover that dust with only 1 layer now? The answer is yes, and it is actually in most cases better quality, because what's happening is this dust that is sprayed or the overspray is really absorbed by the first layer and melted again by the second layer because of the very short time that you have. So let's say you spray the exterior of the car with a first layer. In less than a minute, you're going to apply the interior painting. So that means the exterior of the car is still wet. So any dust or overspray coming out of the atomizer there when you do the interior will land on a semi-wet surface, not dry car body. And then in less than a minute again, you're going to coat on top of that very quickly with a second layer. So there's 2 things. We're sandwiching this, this layer of overspray with 2 wet layers, and instead of covering it, in most cases, we're kind of blending it, melting it into the layer. So I think that answers that question, Simon.
Thank you very much. Yeah, no, that's great. No, that's what I thought, that it would effectively give you a higher build in certain places, but obviously that's something that has to be very carefully looked at. I've got a question from Bangalore in India from Geometric Limited, Mr. Vadivel Murugan. I hope I say your name right, sir. Can you tell us, Didier, about any saving in simulation time on this, such as it with iGrip? Yeah, are you is it really giving us a saving in simulation and program time?
Yeah, that could be another webinar session, Simon, on simulations.
No, absolutely, yeah.
All right, let's talk about that for a second. Simulation, I don't have a lot of that on my presentation. It's a very important part of what we're doing. We are programming less and less with teach pendant. Most of the programming, especially for exterior of the car body, is done with offline programming tools. ABB has developed its own programming tool called RobotStudio, which myself and my team, we are exclusively using this tool now for all our applications. What you'll find with systems from Delmia or from the RobCAD system, it makes good programs, it works, but there's some alignment conversions that needs to be done to transfer the programs. RobotStudio does work directly with robot softwares. So RobotStudio emulates and uses the robot software. So when I'm loading RobotStudio on my computer, I have to load the same software that I'm loading on the robots to make it work. And then the programs are transferred directly. If it works on RobotStudio, it will be loaded and it will work on the robot. So the parameters for the application are usually well defined before, and I am talking about the speed of the robot, the target distance of the atomizer, the index on the path, you know, the distance from one path to the next. This is defined. So what's remaining here is to lay down the path on the car body, staying perpendicular to the surface, making sure all the areas are covered, that there's no overspray. So that's easy to do with offline programming tools. You still need to be a little bit experienced with paint. If you don't know how to paint with a robot, you're going to make programs, but they're not going to be perfect the first time. But the tools are there to make the program. So we have in ABB many programmers that are really experienced into painting cars that are using those offline programming tools. When they are done making a program, I'm going to say I've seen some cases it's 100% done. You just put the programs in the robot and it paints right away. The first car is good. And sometimes a little bit of tweaking. Some areas are a little bit light. Some areas have a bit too much paint, some areas were missing, but the offline programming, I would say now, is, I would say, at least 95% of the work is done offline programming. And also, it's not a topic today, also for interior painting, we're doing it that way.
Thank you. That's great. Thank you very much indeed.
Sure.
Yes, Mr. Nirmal Babu has just left us a message. He's from Ashok Leyland in India. Hello, Nirmal. I was actually in your factory 2 weeks ago with Mr. Ravi. AMS was visiting Ashok Leyland in India, and we'll be writing about that. And they'll be speaking at our AMS India conference. So it's a great place. And although they seem to paint most of the trucks the same color, but I think it's a very nice color. So, regards to Mr. Ravi and everybody at Ashok Leyland. We have a question from Nirmal also saying, have you integrated with Takesha and Dur in India? How is ABB's integration situation in India? Just quite briefly, please, Didier.
Okay, I'm going to first be very honest. I love Indian food, but I've never been in India. And I have colleagues working there that I could inquire with. I have not been involved with many operations in India, so I could not answer that question, Simon. I'm sorry.
Okay, no problem. Well, Nirmal has sent us his email address and he's asking you to definitely get in touch. So you'll have that afterwards. So thank you for that, Nirmal, and thank you, Didier.
Simon, on that note, I have a gentleman from our process team in the USA that has moved to India to support paint activities over there.
Fantastic. Oh, good. Thank you very much. A question from Guillermo Formoso, which he asked several questions really about painting plastic bumpers. What advantages, are there as many advantages for a non-conductive like a plastic as there are for a steel or aluminium body? Can you explain how well does it work, and what do we gain in painting, hang-on parts which are non-metallic?
All right. Bumpers, painting bumpers with electrostatics, it's always been a debate. Should I use it or not? You will not get the high transfer efficiency that you get from a grounded metal parts, for sure. But you will get a much better transfer efficiency than if you do not have electrostatics at all. When it comes to grounding, when you start to spray a bumper, it takes time for the bumper to take the load of electrostatic and becoming charged to the point where it will not have any electrostatic effect. So it's not as efficient, but it's a lot more efficient. In tests that we've done with both solvent-borne and water-borne paint, I mean, we can clearly see a saving between 10 and 15, a bit more than 15% of paint using electrostatics. So this is a clear advantage there.
Right. Thank you. Yes,
sure.
I mean it's obviously still a much greater advantage than using air pressure or pneumatic paint.
Absolutely.
Can you tell us from Mr. Diego Garcia? He asked, is there a way to use the robots using a different gun, of course, for PVC, anti-chip, stone chip, underbody coating, and so on? Is that an efficient use of these? I mean, I'm not sure I quite understand how it would be unless you tilt the body, but perhaps you can tell us if you thought about it.
Yes, I understand the question. Let me reframe that for so those that are not so familiar. On car bodies, we are applying underneath in some areas paint called blackout, stone chip or anti-chip. Those are paint layers that are either here for cosmetic or chip or rust protection. We typically use a spray gun to do that because the expense of an electrostatic atomizer, you never get a payoff on that or a payback on that, because the paint used in those areas are sprayed in small amount, and the paint is very, I would say, cheap, inexpensive material. So the savings you'll get from electrostatic is not worth the expense that you would have to put in an electrostatic system. And yes, you can put any spray gun on those robots to work in those areas. It's absolutely not a problem. Done in many places.
Yeah, no, I must say there are quite a few examples that you might read about in our Automotive Paint Shop Solutions magazine, where even in sealing, in applying seam sealers and so on, there are paint engineers like at General Motors in Europe who don't have robots of your sophistication, and they're having to complete a lot of the sealing operations by hand still, which is dangerous and slow. So I can see that the axis flexibility of the robot is certainly very applicable to all these things, as you say. We've got another question here from Anand Shinder of Tata Motors. He asks, are the examples shown of the footprint optimization, are these realized elsewhere or still in the laboratory? Are they actually, will you be able to show some prospective customers actual case studies of where they are realized already?
Absolutely. I have concrete examples. Many paint lines we have installed in a retrofit. Let me give you an example of a retrofit application where other robot suppliers would spend time telling the customers that it's impossible to install it in the footprint, and at the same time we were showing them a simulation. This is how we are going to do it. So yes, there's a large amount of installations that we've done in recent years that would not have been possible because the booth would have been too small on retrofit, or on new plants. We're saving, I mean, one of the plants we've designed, installed in 2007 here in North America, we're saving 26 meters of booth length per line. 26 meters of booth length shorter than the classic original concept that this customer was going to install. An installation that we're starting up right now, the reduction in length, okay, is in the same area, 30 to 35 meters of booth reduction in length. So there's a significant, and we have examples of reductions of footprint. The numbers are there for us. So there's a few things you have to look at differently, like the concentration of robots is higher. You don't have a robot every 5 meters, you have a robot every 3 meters now because you don't have a rail. So it might appear that the robots are packed against each other, but they are working very well like that. We know how to program them like that. And also you will see some concept where we are using the flash of time to paint the interior that significantly reduce the flash of time. You will see other examples of applications where the robots are doing more than one thing. They're not doing on the interior, exterior, underneath. They're doing more than one application. So to reduce the footprint, in a lot of cases, you have to change a little bit on things on your process. But the numbers and the example, the case, they are there. I could say offhand, I have at least 6 or 7 cases where we significantly reduced the footprint of installations.
Right, thank you very much. So your next step is to have one in at Tata Motors, I think, Didier. And I think it sounds like some encouraging signs from there.
Simon, seems like everybody's calling from India today. This is good.
Well, they have a great thirst for knowledge, and it's a great developing industry there. So, as you know, our next event is at AMS India, which is in Pune, on the 3 to the 5 of December, and we'll be having a major paint shop session there, certainly. We've had another message from Mr. Anand Shinder of Tata Motors, who said, "Can you please send me the email ID of Didier Rual?" I'm sorry, I don't know how to say your name exactly, Didier, but I'm sure that you will be in touch with him directly, I hope, as soon as you can, for sure.
Perfect. Thank you. Thank you, Simon.
Okay. Well, we don't seem to have any more questions coming up. I just wanted to ask one question, which is about energy consumption. I mean, obviously we're saving a lot of space, we're saving time. It's remarkable to be able to use the interior painting time for a flash off and still get a great result with very little overspray and contamination of the exterior layer. But where are you really going to help your customers make savings? If you can outline that in energy, in space, in cost of equipment, utilization of footprint, and so on. You can give us that as a sort of roundup, please, Didier.
Yes. So the major driver for, I would say, paint robotics development today is to have products that are going to reduce the production cost, and that also going to reduce the impact on the environment, and that are going to reduce the footprint of the spray booth. The biggest single source of energy usage on manufacturing a car is the spray booth. The amount of air volume that goes through the spray booth to keep the temperature and the humidity in control when we spray the car, it's big. It's a big amount of air, lots of energy to either cool it off or to warm it up. So when we reduce the footprint by a few square meters over the years of operation, this is millions and millions of dollars. Millions of dollars of energy saved because the booth is 3 or 4 meters shorter. This is something difficult for some project planning to do, to look at the impact on the long run and having the ability to spend the money now to make things a little bit better. But this is really the driver for us. This is what makes that. Our products are of a very high quality, very high performance, and they are driving high efficiency and reduction of production cost. So I will sum up with that. Efficiency, this is what's driving our design.
Right, thank you very much. Yes, we're still getting one inquiry. We've still got one inquiry from India, from Vadivel Murugan of Geometric Limited in India. He said that please name a few plants in which this concept is implemented. I think that probably for confidentiality issues, etc., perhaps if you could liaise directly with Mr. Murugan, that might be more appropriate. Oh, and I've got a question here from Caio Bertolini in South America, here in Brazil or Argentina at Ford. He says, Didier, when you talk about offline programming, do you take into consideration the paint technology being used? For instance, waterborne or high solids paint have a much higher cover power or covering power than other paint technology. This means we do not need to overlap layers so frequently. Is this something that is catered for within RobotStudio, or does it require paint experts' know-how when programming? So I'm sorry, I hope you've got all that.
Yeah.
Perhaps we, yep.
I can answer that very quickly, Simon.
Okay, thank you.
In RobotStudio, there's no real tool that will tell you how fast the robot should go and what's the target distance. This is up to, I would say, process development and process testing. This work needs to be done either with paint suppliers or with experiment testing to figure out exactly what needs to be done. One thing I can tell you is myself and many process engineers, we can just look at the technical data for paint characteristic, and in a few minutes I can tell you how fast your robot will have to go, how much fluorite you are going to need to achieve the film thickness that you want. It's no rocket science. There's only 6 parameters involved into this calculation, and you put them together and you can know exactly how fast your robot go and what's your dispensing rate of paint. And with this, you can easily make a program. When you know how fast it has to go, what's the target distance, what's the index from one path to the next, it's very easy to make the programs from there.
Yes, yeah, I mean, yes, as you say, the parameters are those, and humidity, viscosity, and speed, as you said, and so on, and the build that you want to achieve, yeah. I mean, it seems that, as Caio says, that that it's something that should be within RobotStudio or something like that, but it's, as you say, it is a fairly straightforward calculation, is it?
Yes.
Fairly common calculation, yeah.
And we are providing paint seminars and we are teaching people how to calculate estimate understand and estimate those parameters. There's a little bit of understanding you need to get before you can calculate all of that, but this is something that we are teaching our customers.
Well, I think then you have an interested student there, Mr. Keo Bertolini, as I say, from Ford in South America. So please do stay in touch with him. I think we don't have any more questions now. So if you wanted to round up or anything, I would just say thank you very much to everybody for joining us today. This webinar will be uploaded into our archives and accessible in the future for all of your colleagues who've been unable to attend. So any colleague or somebody that you think would have enjoyed this or would have found it interesting, then you will be able to find it in the archive. You can access this and all our previous webinars on the webinar tab on the AMS web page, homepage. So we thank you for joining us today. I want to say thank you very much indeed to Didier Roy. If I ever get your name correct, Didier, I'm sorry if I get it wrong.
No problems.
Thank you to ABB. I think it's been a most successful webinar, and thank you to everybody that's tuned in from all the car companies and tier suppliers and so on. And we hope you'll join us again for our next webinar. So thank you to everybody. Thank you, Didier.
Thank you.